Okay. Well, hello. I hope you guys had a good weekend. I was the other class, the 102A class, had their midterm, so I was busy responding to all these questions and stuff. So I apologize. I didn't prepare lecture slides, but I'm going to cover, I think, just key parts of the first part of chapter 6 today. Okay. And I'll go over some of the R commands that you need for diagnostics. Well, today will just be diagnostics for multiple linear regression, okay? Now, I don't know how you guys are reading the textbook. I don't know if you just kind of sit there and read through it or kind of skim, or, or I don't know how it's going. But I'll just highlight the stuff that I think are important to know in the textbook, and we'll talk about it in greater detail today. Okay. Well, I hope. Let's see. All right. So with multiple linear regression, we perform diagnostics in a similar way that we do for simple linear regression. Effectively, in simple linear regression, if you think back to that, we checked the residual plots. What we want to do, well, the purpose with diagnostics is we want to make sure that the model we're fitting is a valid model. And that's maybe one of the big key themes in the entire course, is that if the model you're fitting is not valid, then all the inference that you're making from your model will not be useful. Okay. And so your prediction intervals, all of that stuff, just doesn't work anymore. And so multiple linear regression, the same types of concepts hold there, although there are a few key differences. Okay, so one of the big tools that we use, just like in simple linear regression, is standardized residuals. Okay, so we're going to create plots of the standardized residual. So you fit your multiple linear model, plot the standardized residuals, okay? And we can also take a look at leverage points. These are calculated much like they are for simple linear regression. All of these things about outliers and all of that, these all apply. So these are, I think, just like simple linear regression, okay? With multiple regression, however, we have this additional tool called the added variable plot, okay? And then we got these other tools here. But effectively, we want to make sure that our assumption of constant error variance is correct, because if that's not correct, if you got heteroscedasticity, you've got problems. And then and sometimes you collect time series data, and that has its own set of things to worry about. Okay, so here's all of this matrix notation stuff, which I feel like we've covered so many times already. The key being, and I think these results we've already arrived at earlier, we've got beta hat equal to, x transpose x inverse x transpose y as the results of all of this stuff. Okay, we have the hat matrix. Okay, so if you think of y hat being x times b hat, okay, we can replace what b hat is. Okay, we can plug in b hat, and essentially we now have this entire thing. And then so we're just regrouping our variables, and we call this h. Okay, so it's x times b. B is, I can't highlight here. B is from this parentheses to the y, and then we just regroup and say now this is h. Okay, and this is called the hat matrix. And the diagonal elements of the hat matrix are the leverage values of x, of your data points. Okay, so what is leverage? Do you guys remember? What does it measure? It measures x. It measures kind of how far a certain point x is in relation to the other values of x. So if it's kind of in the middle of all the x values, it has low leverage. If this x stands out from the other x values, it has high leverage. Okay? You just have to now generalize this into kind of this multivariate setting. Okay, so keep in mind your x is now not just one predictor, but you've got, I'm sorry, so before it was just these first two columns, now you have p columns, okay? And so, you know, how far is this x from the other x's? Now we have kind of this multi-dimensional setting, all right? So it used to just be very simple. You can kind of just measure horizontally how far x is from the rest of the x, but now you're still measuring how far your point x is from kind of, I guess, the centroid of your data, but it's now whatever, n-dimensional or p-dimensional, okay? So anyway, you got your hat matrix, same thing. As before, they give you this special case, but you don't have to read it because it just tells you exactly what we already knew. Rules for identifying leverage points, it just gives you a rule of thumb. And we just say, take how many dimensions you have, p, add 1 over, and then divide by n, multiply that by 2, and if your leverage is larger than this magical number, it's considered high leverage. That's, again, just a guideline. All of these are kind of just wishy-washy rules, right? I mean, yeah. You know, p-value less than 0.05 is also a guideline, okay? We kind of, we've turned it into like the gold standard of razor that, you know, it either works or it doesn't work, but also that's intended to be a guideline, just like everything else. So you don't have to say this is, if it's, you know, ever so slightly below this, it could still be have significant leverage. Okay. Okay. So this part's important regarding properties of residuals. Okay. So think of your residual as y minus y hat. Okay. We can then factor out the y, okay? So y hat is actually the hat matrix times y. It's kind of funny that you can factor out the hat, but you can, okay? And y is then multiplied by the identity matrix, all right? And so we can think of the residuals as the identity minus the hat matrix times y. Okay. Well, under the assumptions of multiple linear regression, then, the expected value of our residuals is 0. Okay. Yeah, you can look at this. But the expected value of our residuals is 0. This should kind of just be like almost an expected thing by now, okay? And the variance of our residuals is essentially, you know, the variance of this thing, okay? And so the variance of y is sigma squared, but, you know, our matrix is multiplied by I times h, so it's our variance sigma squared times I minus h. I'm sorry, yeah, I minus h. Sigma squared. So again, we're assuming constant variance in our residuals, constant variance there. Okay. All right, and then so if we're looking at individual points, we get rid of the I and we just turn it into a 1 and a little h, and thus the square root of this, our standard deviation, would just be sigma times the square root of 1 minus h. And if we replace sigma with our best guess s, we get this. Okay, so our standardized residual is the residual divided by the standard deviation of our variance. I'm not standard deviation of y. Okay, and this is our estimated standard deviation, and I think we've already covered this part here. Okay, and so our standardized residuals, again, now that we've standardized them, we can kind of get an idea of what's big and what's not big, just like before. So we say, 2 to minus 2, these are pretty large, and then if we if we have more data sets, maybe we push these out to 4 and minus 4. So it's almost the same rules that we had for simple linear regression, but now we are applying in a multivariate setting. Okay, so the book goes through an example, and the key difference between simple linear regression, the standardized residual plots of simple linear regression, and multiple linear regression is that in simple linear regression, if you saw a pattern in your residual plot, it could give you an idea of what was deficient in your model. So if you see some kind of curvature in your simple linear regression residual plot, then you say, oh, maybe there's a quadratic term or something like that. Okay? With multiple linear regression, you can't do that anymore. Okay? You might see a pattern and it might look quadratic, it might look something very clear to you, but you can't then say, oh, what I need to do is add a quadratic term. Okay, that doesn't work in multiple linear regression. And pretty much all of the next pages in the book cover that concept. But the reason why is that with multiple linear regression, if you see a pattern in your residuals, then yes, you can say, my model is not valid. My model is wrong. You can say that. However, you don't know why your model is invalid. Okay? It could be missing an entire other variable that may or may not be quadratically related. Okay? This other variable that's missing, could be the thing that's causing the curvature, and you can't tell just from looking at a residual plot. So there could be other variables that are missing. There could be just a whole bunch of stuff. So with simple linear regression, it was clear, but once you add more than one term, then it no longer works. Okay, and so that's okay. So this says a pattern in the plot is indicative of an invalid model, and then it goes blah blah blah. But then here it says, but the pattern itself does not provide direct information on how the model is misspecified. Okay, and then it goes through all of this stuff, and it says, here we're looking at all these things, and yeah, well, actually, that doesn't tell us anything. They made up a data set, and they said, here we see these patterns, so there's a problem, okay? And then if we, here's another pattern, and it looks like, oh, we got to add all sorts of terms, but it just turns out it's nothing special. It's just we're missing a predictor that's different. Okay, so yes, based on residual plots, we cannot say anything about what part of the model is misspecified. Okay, all of that, just to say that. Okay, added variable plots. These are rather interesting. Okay, So the key here with added variable plots, these are not the plots that we're looking for. We can look at a data set, okay? So this is from our restaurant data in New York City, and we can see, you know, how is food related to price? How is decor related to price? How is service related to price? You know, how is East related to price, okay? And so all of these things seem like they're positively correlated with price. And that's correct, okay? However, I don't know if you guys remember, but when we looked at the actual coefficients of the model that we fit, for the when we included all of these predictors, the food, the decor, and the service actually had, it seems like, no impact on the price, okay? So, you know, how is that the case when, you know, clearly looking at this, it seems like there's a positive linear relationship, okay? Any ideas as to why this might be happening?
Are each graph, the graph that you get from simple linear regression?
Yeah, these are the graphs. If you do simple linear regression of, if you do service versus price, this is what you get. And if you do food versus price, these are just straight, like if you only had these two columns in your data set and you did simple linear regression between these two, this is what you would get. So what do you think is going on here?
There are other factors such as decor and service that affect price other than food. So when we look at all three of the factors.
Yeah, so what we want to do, what we wish we could do, so it turns out that this thing, even though it looks like service and price are related, it turns out service is not significant. And the reason is that for us to see if service in of itself was significant, we would have to keep food and decor constant, okay? We would have to say, we would have to restrict food to some level, decor to another level, and then see how changing service or see how changes in service affect price. But, you know, it's, if you think of restaurants, in general, if you go to a fancy restaurant, all of the things kind of go together, right? Like if the food is nice, then probably the decor is also nice, and you would expect the service also to be kind of nice on the other, nice with it. Or if you know, if you're going to a junky restaurant where you know, the food isn't that great and the decor is not that great, you're probably not expecting the best kind of service. So the thing is the way we have our data, yes, there's definitely a positive correlation between service and price, but that's because as service is changing, these other things, food and decor, are also changing as well, okay? And so to see the true relationship between service and price, we have to somehow freeze these other things, but how can you do that, okay? That's where the added variable plot, this is also known as the partial regression plot, if you look this up, partial regression. And effectively what we do is you well, it's hard to explain here. Effectively, you're going to create a few plots, okay? So if we wanted to do the partial regression plot for service, we create a model where we predict price based on food, decor, and East, okay? So we create a model to predict price without service, okay? And that's going to form our y variables. And then we create a model to predict service based on food, decor, and east. And this will produce our x, well, not our x variables, I'm sorry. So we produce, okay, I have to back up. So we produce a model to predict price based on the other three variables. We produce a model to predict service based on the other three variables, okay? And then we look at the residuals of this model, where we've predicted price based on the other variables, and we look at the residuals where we've predicted service based on the other models, okay? And then we plot the residuals of the first model versus the residuals of the other model. Can you keep all of that in your head?
It'd be easier if you write down.
Yeah, let's write this down here. Okay, so let's say, so we create two models, okay? Model one, predict price. So this is, added variable plot for service, okay? And then the full model is price as predicted by food, decor, service, and east, okay? So model one is predict price based on food, decor, and service, okay?
East.
I'm sorry, food, decor, and east, you're correct, okay? And then create standardized residuals, or maybe just the residuals. I don't know if it's standardized or not, okay? And then model two predict predict service based on food, decor, and east. And then we create the residuals, or standardized maybe. And then lastly, we plot the residuals from model one versus the residuals from model two. And this is how we make an added variable plot for service. So let's just think, what if I had two columns that were identical, okay? So what if service happened to be either a linear combination of food, decor, and east, or service was just, a decor number two, okay? It was just basically the values in service were exactly the same as decor, okay? What would this model produce? If we were trying to predict, if service could be predicted based on food, decor, and east perfectly, what would this produce? Or what would our residuals look like for this model?
Like a flat line.
It would be flat, right? If we can predict service perfectly based on these other three predictors, our residuals here would be a flat line, okay? There would be no difference between the residuals. So then if I plotted this versus this, would we see any kind of relationship between the residuals here and the residuals here? No, because there's no variance in here that can be used to make any kind of conclusions about the residuals over here. Okay, so if we keep that in mind, then we can see how having a variable that just correlates super highly with the other variables might not give us any added information for price, okay? And so when we look, if we do that, this is the variable added plot. So this is the one that we're looking at, okay? So we're looking at price versus the other variables and service versus the other variables. So this should be residuals from service. So I guess they're not standardized here. So we're just looking at the residuals based on the others and the residuals here based on the others. And we see that including service, doesn't produce that much extra information on here. However, you know, if we were to remove food and add food, we see, oh yeah, there's actually some information there. If we, you know, removed decor and added decor, things like that, we see adding decor into, you know, plotting the residuals of the other things, predicting decor and the others predicting price. This actually adds some information to our graph, and so this is significant. Okay, over here when we produce this plot, apparently these are high leverage points that might be something to investigate, because this might have a strong influence on this residual line that we're seeing. Okay, and in fact it does say that case 117 was a restaurant called Veronica, which had very low scores for decor and service. However, they had a high food rating with, I guess, a moderately high price that, you know, put their residual up here for price. Okay, and then case 168 was another one with low scores for decor and service, but had a high food score. I guess a relatively low price. Okay, I would think this would be high. I think this is supposed to say high price because it's the residual for price is positive, right? So that I think that should say high price. Okay. All right, so anyway, this is kind of funny. This is a
Crapshoot.
It's a crapshoot, right? All right, but you know, we all have our favorite restaurants that maybe you say the food's great, but everything else kind of is a little iffy. Okay, but those are added variable plots, and let's look at their creation in R. Where did they go? Okay. Okay, so there's just a nice little function in AVP. I mean, in the package package car. So so in R, you just go, you call library car. If you haven't installed it already, you're gonna have to install it, and then you fit a model. So I have to get my New York City data here. Oh, is this the folder I want? Let me just make sure. Yes, New York City. Okay. I'm gonna do read.csv, so I'll call this okay, and so we're going to create our model, which will be not model, linear model. We're modeling price as explained by food and decor and service and east, and our data is New York City. Okay, and all you have to do is you just specify the what? This doesn't work. Why is this not working? Hang on, sorry. Added variable plot R. AV plots. Oh, they've updated it. Oh. New York City $sign service. Sorry. No. Okay, that's apparently you just do this squiggle. Okay, and so it plots it, and we see there is no, this line is totally flat, revealing that it's not adding anything. Okay, but if if we did something like food, we get this, and then maybe this identify points. I don't know if this is a. Apparently it's not the correct parameter to use. Okay, well. Maybe I can use identify. No, I cannot. Okay, I apologize. Okay, but yeah, you can, I guess the command is AV plots, and you just pipe in the model and the variable that you want to test against. Okay, we can do it ourselves also if we wanted to follow these steps regarding creating the full model based on everything else, and the standardized residuals, and then creating or not the residual, not standardized, just the residuals, and plotting those against each other. Now I'm nervous that this is not going to work, but all right. So if I create M2, so this will be our model without service, where we're predicting price based on food, decor, and east. Okay, and then we can call residuals of M2. Whoops. We'll call this resid.m2. And then, I guess, for lack of a better name, we're going to call M3, and we're going to predict service based on food, decor, and east. Okay, and we got residuals of M3. We'll call this .m3, and then we'll plot resid.m3, our x, against resid.m2. Does that look exactly the same as our AV plot for service? I hope. Yes. Okay. So sometimes it's risky doing things on the fly here, but yes. So you can fit the model and then fit the residuals and plot them against each other and look for some kind of relationship. And so in this case, you could do just to kind of get that fit line, you would have to do lm of residuals M2 as explained by residuals M3. And then, so we'll call this AV model. And we'll ask the summary of AV model. Okay, and it says pretty much you've got no slope and nothing is special about this one. Okay. And so these are added variable plots here. All right. I am in the process of writing your midterm exam, which I will release on Friday. We have a department meeting on Friday, okay? So I won't have lecture that day, okay? So I guess on Wednesday I'll try to have the midterm complete, and then on Wednesday I'll talk about it, but then, well, maybe I can release it Friday morning, but I don't want to release it too early and give you, I'm just afraid if I give you too long, then it opens up the temptation to talk to each other. So I feel like if I just give you the weekend, you know, I mean, I don't want you guys to be talking to each other for the midterm. So, so anyway, I'm trying to write the midterm exam. I'm wrestling between how open-ended it should be, because I truly believe data analysis is an open-ended venture, but if I leave it too open-ended, then I get answers that are all over the place and it's very difficult to evaluate. On the other hand, I don't want to be so restrictive in that, then it's just like, here, I don't want it to just be like, how do you type this function into R and get what the plot you want? Because that's, in my opinion, not very useful to you as you guys are trying to learn this idea of data analysis. So, yeah, if I'm going to err on one side, it's probably going to be on the slightly more open-ended side, and that means, a lot can be done, and the grading is then going to be a little bit subjective, and I know that's hard for some students to deal with, but it's kind of like, well, I don't know. Do you guys still have to write essays? Do you guys take courses where you still have to write essays for them? Yeah. Sometimes, not really, right? Like, I didn't like essays because it felt super subjective on the grading, right? You just write this thing. But data analysis is kind of like that, in that, you're presented with a problem and you explore, and people will come to different conclusions and have different things to highlight and point out. And I'm going to have to try to find some way to evaluate you guys fairly and clearly on your thinking about the data. So I hope you guys will be merciful on me and regarding just your opinions of the midterm exam. But I'm hoping it'll be interesting, and I'll try to avoid too much craziness in the data. I'll keep it fairly, I don't want to say clean, but just, it'll be interesting to say, okay? So we'll end there, just covering about the added variable plots. I might just briefly mention transformations, but I don't want to get too heavy into this, just because it's a deep rabbit hole. So we'll cover it in its entirety eventually. So we'll end a few minutes early today, and I'll see you guys on Wednesday.